Welcome to the Explainer. Today we're going to look up, way up, at the incredible secret that lets these massive skyscrapers kind of dance in the wind without tipping over. It's an amazing feat of invisible engineering, and we're about to pull back the curtain.
Have you ever just stood in a city, looked up at one of those giants, and wondered, how does that not just fall over? It seems to defy physics. Well, the answer isn't just about having a strong foundation. It's a super clever bit of engineering hidden way up near the top. So, to get to the solution, we first have to really understand the problem. And you can think of it like a secret dance. Every tall building has its own rhythm, its own natural sway.
See, every time the wind picks up, or the ground shakes even a little, a skyscraper starts to vibrate. Now, most of the time, you'd never even feel it, but that constant motion can be unsettling for the people inside. And in extreme weather, it could even be dangerous. So to solve this, engineers gave the skyscraper a dance partner, something designed to perfectly, and I mean perfectly, counteract its every move.
And that dance partner? Well, that's the hero of our story today. It's this incredibly elegant piece of engineering called a tuned liquid column damper.
At its heart, a TLCD is just beautifully simple. Seriously, it's just a giant U-shaped pipe, and it's partially filled with a liquid. Usually it's just plain old water. But the real genius here is that it's a completely passive device. It doesn't need any external power, no computers, no motors. It literally uses the building's own motion to cancel itself out.
The way it works is so intuitive, it's brilliant. Okay, so imagine the building sways to the right. Because of inertia, all that water in the giant U-tube sloshes to the left. And that huge moving mass of water creates a powerful counterforce that pushes back against the sway, calming the entire building down. It's a perfectly timed, perfectly opposite reaction every single time.
But, it's not as simple as just sticking any old tank of water up there. To make this work perfectly, engineers have 4 critical tuning knobs that they need to adjust to get the damper dialed in just right for each specific building.
The first and, honestly, the most important knob is frequency. Every building has a natural frequency, a rhythm it likes to sway at. The water in the damper has to be tuned so it sloshes at that exact same frequency to effectively push back. Engineers nail this perfect timing mainly by adjusting the total length of the water column in that U-tube. If that timing is even a little bit off, the damper is basically useless.
Okay, so once the timing is set, the next question is about power. How much water do you actually need? That brings us to our second knob, the mass ratio. A pretty common rule of thumb is to use a mass of water that's about 1 to 2% of the building's own mass. And of course, it's a trade-off. More water gives you more of that counterforce, but it also adds a lot of weight and takes up valuable space. But timing and mass aren't enough on their own. You also have to control the slosh. And that's our third knob, damping. To do this, engineers place an orifice, which is really just a fancy word for a bottleneck, in the horizontal part of the tube. As the water gets forced through the smaller opening, friction creates heat, and that literally dissipates the vibration energy right out of the system. This controlled slosh is what truly makes the whole thing work.
And the final piece of the puzzle isn't just about what's inside the tube, but the shape of the tube itself. This aspect ratio, basically how long the horizontal part is, acts as a final fine-tuning dial, affecting the damper's sensitivity and its overall performance.
All right, theory is great, but let's actually see how these knobs work in practice. We're going to design a quick damper for a really simple one-story structure, just to see how the numbers add up in the real world.
Okay, so let's start with our building's mass. We'll say it's 10,000 kilograms.
For our mass ratio, that's tuning knob number 2, we'll just use a pretty standard value of 2%.
A little quick math tells us we're going to need 200 kilograms of water. To give you an idea, that's about 53 gallons. So a decent amount, but not huge.
But here's the part that just blows my mind. To hold that water and get it to slosh at the right frequency, our calculations tell us the U-tube itself needs to be 1.13 meters wide. Think about that for a second. That's nearly 4 feet in diameter. And this really shows you the real-world challenge. These elegant solutions can take up a massive amount of space.
So here it is, our final design. We've got our mass, our liquid column length, that huge tube diameter, and this thing called a head loss coefficient.
That's just the technical term for our bottleneck we talked about, the part that actually creates the damping effect. And just like that, all 4 of our tuning knobs are set.
You know, when you put it all together, what you have is a solution that is truly genius in just how simple it is. It's a real testament to clever engineering.
So why are these things so clever? Well, it really comes down to a few key things. They're passive, which means they work even in a power outage, exactly when you might need them most. They use water, which is about as cheap and available as it gets. They can even pull double duty as the building's emergency water tank. And at the end of the day, it's just a beautifully simple, elegant solution to a really complex physics problem.
It really makes you wonder, doesn't it? The next time you're in a city, look up. Think about all the other invisible feats of engineering that are quietly working all around you, solving these huge challenges just to keep our world running smoothly and safely. What else is out there that we never even get to see?